Yeah. Right, so let me jump straight into it. So we need to look at absorption and reflection of thermal radiation. So I'd like somebody to read this for me. Zachary, you read this for me. Absorption and reflection of thermal radiation.
Alright. Materials of various textures and color absorb, emit, and reflect different amounts of heat. Note that good absorbers are also good emitters of heat. Would a Caribbean house roof be a good reflector or emitter? What about a car radiator or a windscreen shade?
So let me think about it, right? Zachary, do you want the heat to enter in your house? Do you want that?
Nasty.
So would you want to emit the heat? By the way, you could think of emittance and absorbance hand in hand, right? So when I say
Mm-hmm.
emittance, think of absorbance. Do you want heat to be emitted or absorbed in your house?
Mm-mm.
No. So would you use a like most house roofs, right? It's a kind of silver, right? Kind of silver.
Yes.
So if it's silver, will it reflect heat or it absorb heat?
Reflection.
Right, reflect. Um, what about a car a windscreen shade? How does that look? A car windscreen shade,
Shiny. So
shiny. Now the car radiator is a bit of an interesting one. This is kind of a debate, but most car radiators are what color? Do
black,
you all know?
gray, black. Something.
Yes, gray and black. The reason for that is because you want to absorb as much heat from the engine as possible and dump it out. And isn't black a good absorber of heat?
Mm-hmm.
So think about it, Zachary, and that makes sense. If you want to extract heat, you want to pull heat from the engine out, you need to absorb that heat. So you wouldn't use silver, right? Silver
Yes.
would just silver would just reflect the heat back into the engine, and you wouldn't want that.
Mm-hmm.
Karina, if you want to cool a car and you want to remove the heat from the car, Karina, can I hear Karina? But here's Zachary. So these are the properties you need to know. Good absorbers are of a black color, dull matte, rough texture, small surface area. And I'll make a note here. Good emitters, I was saying good absorbers are also good emitters. Right, so Zachary, read that table for me.
Good absorbers are black color, dull slash matte, rough texture, small surface area, and good reflectors are white in color, shiny or glossy, smooth in texture, and have a large surface area.
Nice. Right, so as you can see in this diagram, if you place a hot metal block in the sun and you paint one side black, you paint the other side shiny white, you notice the temperature on the left side is a lot greater than the temperature on your right side. That's From this we could observe the passive properties that play a role in absorption of temperature. Once in absorption of temperature, we could see how the passive properties play a role in the conductivity of heat, thermal conductivity. All right. So does everybody understand this? Good absorbers and good reflectors. You need to know these properties.
Yes, sir.
Yes.
Okay. Let's look at a solar water heater, right? There was a question. Let me go to that question. I'm sure they were talking about. So there was this question, guys. Zachary, could you explain to me what's going on here? Like, we didn't do it officially as yet, but I just want to see if you have some intuitive understanding of it. So notice we have a glass plate over here from
Mhm.
the last class. From the last class, what kind of rays does the sun emit? Short wavelength or long
Yes,
wavelength
short,
IR
short
light?
wavelength.
Short wavelength. So the sun is emitting short wavelength IR light. That's gonna pass through the glass, so it's
Yeah, it will
gonna,
pass through the glass and it wouldn't
right?
be able to exit.
It would not be able to exit because think about it like this: wouldn't that short wavelength radiation heat up everything on the inside?
Yep.
But when it's the objects that are heated, it's gonna be less strong than a short wavelength. It's gonna have less energy than a short wavelength ray. So when it's emitting back the heat, it's going to emit back a very little amount of heat, and that heat is not going to be strong enough to pass through the glass. So the short wavelength enters, right, heats up the objects on the inside, and the objects on the inside would emit long wavelength radiation, which cannot pass through the glass. So Zachary, the heat is going to get trapped on the inside. Now the whole purpose of this thing is to heat water. They call it a solar water heater. So as you can see, we have water flowing through this. So water would pass through this thing, water would pass through like that, and then it would exit back somewhere. So Zachary, can you see that if you have water in these pipes here, and you have a black collector plate here and a cup and it wrapped in a copper tube, right? So the water is passing through a copper tube. Wouldn't all that heat get conducted via the water and heat up the water?
Yes, sir.
Yeah, so you understand that, right? And you think you could tell me why we have a black collector plate of all things?
So because the black would absorb the heat best.
Right. Black is a good absorber and emitter of heat. So it's going to absorb the heat and it's going to emit it to the copper tube.
Yeah.
Right. Insulation. Why am I putting insulation at the bottom? Do I want my heat to escape?
Nah, sir.
Nah. So that's why you'd put insulation at the bottom. You don't want that heat to escape to the surroundings. And why are we using copper tubes for the water to run through? So water is running through these copper tubes. Why do we select copper tubes of all things? Why not plastic tubes? Why not PVC?
Yeah.
What's so good about copper?
A good conductor.
It's a really, really good conductor of heat. So when the inside of this solar water heater heats up, right, and this black surface gets really hot, the copper tube is attached to the black collector tube. The black collector plate.
Will get
So
hot too.
exactly, the heat from the black collector plate will be conducted via the copper tube, and that's going to heat up the water that's inside via conduction. Make sense?
Sense.
So that's the whole working property of a solar water heater. So you can see it over here. Short wave radiation from the sun passes easily through the glass and is absorbed by the black surface. The black surface becomes warm, but because it is much cooler than the sun, it re-emits the energy as long wave infrared radiation. Cooler objects always emit longer wavelengths of radiation. So long wave radiation cannot escape back through the glass, so it becomes trapped and the temperature inside increases. They wanted us to explain the greenhouse effect. Right? So let me know if you understood this entire question.
Yes.
Okay, Sheena, did you understand the entire question? Sheena and
Yes,
Karina,
sir.
I'm not hearing you guys.
Yes, sir.
Yes, sir.
Okay, so Karina, is a black surface a good emitter of heat?
Yes.
Yes. What's a better absorber of heat? Black dull or black shiny?
Black dull.
Okay, great. You understand. Nice. Right, so I would have gone through this with you already, right? A solar water heater. But Karina, just read it back one more time and then we're gonna move on. Read solar water heater for me.
Solar water heater. The purpose of a solar water heater is convert solar energy into usable heat energy. It consists of a solar panel, water tank, and insulated frame.
Right.
The black
Karina, why would you want to use an insulated frame? What does insulate? What does a good insulator do?
Trap energy or trap heat.
Yeah. And do you want your heater, if you want to heat up the copper tubes, right? Do you want the heat to escape to the surroundings, or do you want the heat to be absorbed by the copper tubes?
No.
Yeah, you don't want the heat to escape, right? You want it to be absorbed by the copper tube. Mm-hmm. Right? So read the black copper pipes now.
The black copper pipes absorb any radiated heat from the sun and conduct the heat into the flowing water. The glass pane mimics the greenhouse effect that traps heat inside.
Right. So, Karina, you understand that the long, what was it? You understand that the short wavelength radiation from the sun will enter easily. It will heat up everything on the inside, right? It will be re-emitted as long wavelength radiation, but that can't pass through the glass, so it gets trapped. And then the black collector plate gets really, really hot. And since the copper tube is attached to the black collector plate, the copper tube heats up and the water flowing through the copper tube gets hot. Understand?
Yeah.
So you can explain it back to me fast, like in 2 minutes.
The glass plate takes in the heat from the sun
Okay,
and
what kind of rays does the sun emit? You have to tell me that. That's a mark. You need to tell me. Short
the
wavelength, long
short
wavelength.
wavelength.
Right?
Short wavelength hit the glass and then the black collector plate absorbs the heat energy,
Right?
which
And
the insulator traps. So um the water from the copper tubes can get heated.
okay, good. But you need to also mention that when the short wavelength radiation enters, it heats up everything on the inside, right? And what's on and the components on the inside is going to then re-emit long wavelength radiation. But Karina, can the long wavelength radiation pass through the glass?
No.
No, so you need to mention that. You need to mention that the heat on the inside will get trapped because long wavelength radiation can't escape. You need to mention that, right?
Okay.
So all that you need to mention in the answer. Right, so let's move on. Right, convection currents. Do you all remember what convection is?
The when the air recycles the heat and the coldness.
So say that a little better. Cold air. What does cold air do? Does it rise or does it sink?
Cold air sinks and hot air rises.
It's the same concept for water, right? Because air is actually a fluid, believe it or not. So, what do you think cold water would do? Sink or rise?
Sink,
And hot water would?
rise.
Right. So, Karina, if this is the heater, right? If this is the hot plate, then the water exposed to the bottom would get heated faster, correct?
Yeah.
So, in which region would the water be at a higher temperature? Region 1 or region 2?
Region 2.
Right. This water is going to get heated really fast. What does hot water want to do?
So can you repeat?
I say this water will get heated very fast. And what does hot water want to do?
It
Does it
wants
want...
to rise.
Right. So it will rise and it will push the cold water from region 1 downwards. Understand?
Yeah.
And when this cold water comes into contact with this region again, it's going to heat back up. Agreed?
Yeah.
And remember how the hot water went to the surface? If it goes to the surface, is it going to cool or is it going to get hotter?
It's going to cool.
Yeah. And so the water that was pushed to the bottom now is gonna get hot. It's gonna rise. The hot water that was pushed to the top, right, is now gonna come back to the bottom, and it's gonna just keep recirculating. Do you understand?
Yes, sir.
All right, Zachary, do you understand the process? 100%.
Yes, sir.
All right. Question. Could you tell me another application of convection currents where you also see it? What's another use of convection currents? Come on, Zachary, do you know any other examples where convection currents would be at play?
No, sir, I don't think so.
All right. Do you have... Okay, that's a dumb question. Obviously, you have an oven, right?
Yes, sir.
Okay. And okay, so we understand that hot. What does hot air do?
The hot air rises.
What does cold air do?
Sink.
Right. In your oven, right? And how your oven does work is that it have a glass door on the outside, so you can see what's inside, right? And to the bottom, you have a bunch of burners,
Mm-hmm.
right? So the air at the bottom, right? That's gonna get heated first. And when it gets heated, what is it gonna do?
It's gonna rise, sir.
Right? And they're gonna push the cold air to the bottom. And I don't know if you ever open an oven, but you just feel the heat like rolling. Like you just feel the heat moving. I don't know if you ever feel that before, did you?
Yes, sir.
Yeah, that's because in the oven there's convection currents at play. So that's another example. Igloos are another example as well. Right? So this is a little explanation. So the diagram above shows a metal pan placed on a hot plate. The objective is to illustrate the movement of water molecules inside the pan. To determine this, we must answer the following questions. How does the heated water molecules move? So, guys, when you heat something, doesn't the material and the molecules gain kinetic energy? Karina, when you heat an object, doesn't the molecules in the object gain kinetic energy?
Yeah.
And when they gain kinetic energy, they will start to move about less or more.
Move about more.
Right, because they get the energy. When they get energy, they feel to sit down, they feel to move.
To move.
Exactly. So when you heat the water, right, they rise as they spread out and become less dense. They gain kinetic energy, so the molecules start to spread out, and the water at the bottom actually becomes less dense, right? Now, when the molecules reach the surface, what would happen? So the more energetic molecules would leave the surface. Do you all know which process is that? Which process is that by which by which the more energetic molecules would leave the surface? Do you all know that process?
As evaporation, sir.
Yeah, that's evaporation, right? Because evaporation only happens at the what? Where does evaporation happen at?
The surface.
Right. 3. What happens to the temperature of the surface after? So the molecules with the most energy will leave the surface, and as such, it would take heat away from the surface. So Zachary, in doing this, the water at the surface is going to cool down, right? So as heat is lost, the temperature of the surface decreases. Do we understand this?
Yes.
All right. And number 4, how can one prevent heat from escaping from the pan? I think that's obvious. And you would just place a lid on top of it, like a glass lid or something?
Yep.
Yeah. Right? What do you think is better to use? A glass lid or like a wooden lid?
A glass.
I would say glass. Because wood is kind of porous and the heat could escape through the pores of the wood. And glass is better. right? So do we understand convection currents?
Yes.
Yes, yeah.
Okay, like I say, I send these notes after class, so I believe you guys will copy it down and make the appropriate notes, right? The whole purpose of class is just to understand the whole concept. So if you forget something in the exam, you will be like, oh, we kind of went through the concept. Maybe I could come up with something, right? It's to actually understand what you're doing, right? So Zachary, let's go through sea breezes. So sea breezes are actually another example of convection currents. So let's check out the diagram we have below. So Zachary, what's happening over here?
So that's the convection current in the sea.
All right. So you think you could explain it?
Um, so since the air by the ocean is cooler, it sinks, and the air, that's I don't think I can explain that good.
All right. All right. So the ocean, and we could like I'll ever notice something that the sun could be how hot, and the ocean will still be cold. Karina, you ever notice that? Like they did like it real hot on the beach, but the water
Yeah.
in the sea, it's still
It is
relatively cool,
last
right?
this is the same example I was giving you last week when you asked me about the convection.
Oh, this was the example you was given, man.
Yeah, but it had like a lighthouse to measure the height of it.
Oh, this is like this is not an obvious example, but it is an example. But the most obvious examples would be like convection currents in boiling water or convection currents in an oven. This is like a less obvious one, right? But Zachary, the ocean is a lot cooler than the surroundings, right? So when wind blows, doesn't the think about it like this. Wouldn't the most energetic particles at the sea level leave through evaporation?
Yes,
Right, and then the wind will pick that up. So that's going to be cool air, actually. That's going to be cool air. So the ocean is cooler, so air loses heat and it would sink, right? So when air comes close to the sea level, it's going to be cooled. Now, cool air would sink. Now, as that cool air reaches the land, what we know about land, and the sun emits short wavelength radiation and it heats up everything. It heats up the land. Now, do you think the emitted heat is going to be large or small?
small.
It's going to be small, right? But it's still emitting, the land is still emitting heat, correct?
Yes,
So when the cool air passes the land since everything on the land is a bit warm, it's going to re-emit heat and it's going to heat up the air a bit. And when it heats back up the air, what was the air going to do?
so it will start to rise.
It's going to rise, right? And then as it passes over the sea, it's going to get a bit cooler and it's going to come back down and it's just going to keep repeating. You understand?
Yes,
So at the sea, so like if air is passing over the sea, it's going to be cooler. And you understand why. It's because water actually has a very high specific heat capacity. So you need a large amount of energy to actually heat up a body of water compared to land, right? So, Zachary, the temperature of the sea is going to be a lot cooler than the temperature of land. So this is going to be cooler and it's going to be hotter. So when the wind passes over the sea, it gets cool. As it passes over the land, it's going to get a bit warm, right? The warm air is going to rise, and then as it passes over the sea, it's going to get cooler. Then the whole process is going to repeat itself. You understand?
yes,
Okay, nice.
So this is why when the earth gets so close to the sun and we're on all the lands, we should become mermaids.
I don't think we're just going to become mermaids overnight, you know, Karina. if anything, we go die by then. Like, and it could take like millions of years for that evolution to happen. If it will. I'm being realistic here. I don't think that would happen overnight. But Karina, I guess you want to be a mermaid.
Yes, sir.
I'll ever watch Pirates of the Caribbean.
Of course.
Zachary, what about you? You ever watch Pirates of the Caribbean?
Yes, sir.
You remember Will Turner and the Mermaid? Don't you know about that? It wasn't. It was Will. It was Will Turner. It was like somebody else. No, it wasn't Will Turner. It was some other person. Some guy was in love with a mermaid. You know what I'm talking about?
Yes.
Yeah.
Which one was that? Dead Man Tell No Tales or something? Like which one was that with the mermaid in it?
I don't remember.
I don't remember
Me
myself.
neither. I don't remember them by name. I just watch.
Okay. So, guys, we are officially done with aspects of thermal physics, right? And let me give you all an introduction as to what we're going to do next by using the same example. So, Zachary, you would have seen me talk about specific heat capacity. What do you think heat capacity of a material is? A material of a substance. What do you think heat capacity is? I'll see name suggest.
How
What do
much
you
heat? How much heat the item as the substance can hold?
Okay. So what do you think could hold more heat? The body of water in the sea or the mass of land?
See,
Now,
the body of water, you see.
exactly. Because let's think about it, Zachary. The short wavelength radiation from the sun, it hits the land, right? It hits the mass of land. Does the mass of land get heated quickly?
Yep.
Does it lose the heat quickly? Think about night. Think about when night hit. Think about when night reach.
Well, yes.
Yeah. Do you think the heat capacity is very, very large to be able to like get heated fast and then lose your heat fast?
Mm-mm.
No. If Hey Zachary, if you heat this, if you were somehow able to heat the entire body of water to like let me just say 70 degrees Celsius, you think that gonna lose that heat easily?
Mm-mm. Sir. Now, sir.
Nah, that gonna remain like that for a while. A while. And another way to think about it, if the sun is so hot and it should heat up the sea, but does it heat up the sea though?
Not really.
Not really. And that's because you need a very large amount of energy to actually change the temperature of water. So that's what it means to has a very high specific heat capacity. It means that the body will be able to hold a very high amount of heat. And additionally, it means that you need a large amount of heat to make a change in temperature. So that's specific heat capacity. So Zachary, you feel like you're okay to move on to a new topic now?
Yes, sir.
Well, the new topic is specific heat capacity, right? Karina, I want to make sure you understand that as well. Karina, does it take a little amount of energy or a lot of energy to heat up the sea? What would you
A
say?
lot. Like
A lot,
a
right?
lot.
Because does the sun even phase the sea?
No.
Some of the No, right? Does the sun phase the land? Does the land get hot because of the sun?
Yes.
Yeah. So if we comparing them, right? Which one do you think could hold more heat? Land or the sea?
The sea.
The sea, because it take a lot more heat to heat up the sea. And Karina, if you're taking tons more energy to heat up the sea, wouldn't that mean that you have tons more energy stored in the body of water?
Yes.
Yeah. Karina, you think land, you think you think objects on land, right? Do you think they retain their heat for a long period of time?
No. It depends on the object.
It depends on the object, right? But most objects don't. Say for instance, I heat up something on land. I put it inside, leave it for an hour. When you go to touch that object back again, will it be hot?
Probably not.
Probably not, right? If you leave a toy car out in the sun, right, and then you bring it and put it inside your house in a cool, shaded region, if you leave that for an hour, is that still going to be hot?
No.
No, let me look at the water now. If you had a really, really hot cup of tea, like real hot, right? Or you have a big pot of water, and the water in that pot real hot. After an hour, and it might still be a little lukewarm or like a little warm.
Yeah.
Yeah. So you could clearly see that the body of water is actually storing more heat. Right? So there's a higher heat capacity. So we're gonna look at specific heat capacity now. So let's do some analysis here. Right? Now, when we're talking about anytime you see the words specific, please know that we are referencing mass. And how much mass? 1 kg. So anytime you see the word specific, we are dealing with 1 kg of a substance. So Zachary, I want you to look at sample A. Tell me the properties of sample A. What's the mass?
1 kilogram.
What's the temperature before heating?
30 degrees Celsius.
What's the temperature after heating?
31 degrees Celsius.
All right. And can you see that we are applying the same power to both samples?
Mm-hmm.
Nice. What's the properties of sample B, Karina?
Mass is 1 kg. Temperature before heating is 30 degrees Celsius. Temperature after heating is 32 degrees Celsius.
Okay, so Karina, just by and Zachary will tell if she's correct or wrong. Karina, which sample do you think got hot faster?
Sample B.
Sample B. Which one do you think would take more energy to get hot?
Sample A.
Which one do you think could hold more heat then?
Sample A.
Exactly. So sample A would have a higher specific heat capacity because it would take more energy to change the temperature. Right? Zachary, do you understand this example?
Yes.
Okay, guys, I'm not on my laptop, so I can't see participants. So if you have anybody else in class other than Zachary and Karina, let me know. Shayna, I'm not sure what's going on, but talk to me. Let me know if you're still there.
Yes, sir. I'm here.
Okay, I'll start asking you questions, and I didn't know. Right?
They
So,
have Jaden too.
okay, Jadon, you
Yes,
there?
I alive.
Jadon, you're talking to my boy. You gotta unmute and be like, hey, ho, 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 Merry Christmas or something, Happy birthday or something.
Happy birthday, sir.
Today's my birthday. My birthday's in 2 days. But thanks.
No problem.
All right. Yeah. So Jadon, right now we're looking at specific heat capacity, and it's the amount of heat a substance could hold, or in other words, it's the amount of heat that you would need to change the temperature of something. So Jadon, let me give you some examples fast, right? I want you to compare water to a toy truck, right? I know, interesting example, but Jadon, let me just say heat up a cup of water, right? Heat up a
Yeah.
cup of water. And not that water real hot. Let me just say you take that toy car and you leave it in the sun, right? So both the water and the toy truck is hot, right?
Yeah.
So you bring both of them inside and you place them side by side in a cool shaded region. Which one is going to retain its heat for a longer period of time? The hot cup of water or the toy truck that was heated?
The water.
Exactly. So would you say the water has a higher specific heat capacity or the truck?
The water.
Right, because the water could hold more heat.
Mm-hmm.
Right. So if you look at this example here, we said that sample A had a higher specific heat capacity than sample B. And the reason we said that was because in the same time and using the same power, sample A heated, the temperature increased by a smaller amount compared to sample B. Sample B increased by 2 degrees Celsius and sample A by 1 degree Celsius under the same time and the same power. Right? So in other words, sample A would require more heat to change the temperature. So it has a higher specific heat capacity. So Shayna, let me know if you understand that. Shayna?
Yes, sir.
All right. Cool. So Shayna, I want you to read this just to summarize. Read that for me.
Observe the diagrams above. The same mass, 1 kg, of two different liquid samples are placed in beakers A and B. Both samples had the same initial temperature, 30 degrees Celsius. Both beakers are heated for the same time, 60 seconds, with the burner set at the same power, 70 watts. However, at the end, the final temperatures differed.
And just remind me, Shayna, which one differed by more?
Which one had more heat capacity?
And which one was the temperature? Okay, which one had a greater change in temperature?
Sample B.
Right, so that has a higher specific heat capacity or lower heat capacity?
Higher.
Nah, lower. I catch you there, Shayna. Shayna, if sample B is getting heated, like the temperature is changing at a faster rate, right, compared to sample A, doesn't that mean it needs less energy to heat up?
Oh, yes, sir.
Yeah. Sample A, the temperature is changing like minimally compared to sample B. So that means for sample A, if you want to change the temperature by 1 degree Celsius, you need more energy. You understand? So sample A has a higher specific heat capacity.
Understood.
Yeah, sure. Tell me if you're
Yes,
sure.
sir.
Okay, taking your word for it. So I need you all to copy this down. Need all to copy that down. These formulas here, you need to know. All right. So Jalen, I'd like you to read this definition for me. Jalen. Okay, I'm not hearing Jalen. Karina, you can read this for me.
The specific heat capacity is defined as the amount of heat required to change the temperature of 1 kg of a substance by 1
Do you
Kelvin.
know what? Okay. Clock it, Karina. You remember what K means? Big up you. Big up you. All right. I remember how to convert from Celsius to Kelvin, by chance.
300 and no 237.
Nah,
73.
73.
It's,
Karina,
it's
I just make that
73.
mistake sometimes, I just say
Yeah.
237. It's 273. 273.
So
Yeah.
I don't even know what I put on that paper because I changed it to Kelvin. I think I put 237.
Oh, shucks. We RIP. Well, if physics is that error carried forward, so you might still get some marks. All right. Yeah, so Karina, specific heat capacity is the amount of heat energy required to change the temperature of 1 kg of a substance by 1 Kelvin. Remember, I told you guys, anytime you see the word specific, we're dealing with 1 kg of mass. That's what we're dealing with. Anytime you see the word specific. All right, so specific heat capacity is the amount of heat you need to change the temperature of 1 kg of a substance by 1 Kelvin. Yeah. Zachary, do you completely comprehend what specific heat capacity is?
Yes.
Okay. Shayna, what about you?
Yes, sir.
Shayna, I presume you do this in school already or not?
No.
No? Okay. All right. So as soon as you all have this, as well as the formula for specific heat capacity copied down, let me know, right? Karina, are you nearly finished copying down everything?
Yes, sir.
Okay, cool. Shayna, what about you?
Yes, sir.
Okay.
I finish.
Okay, cool.
Yes, I done too.
All right, it would seem that everybody is finished. Okay, nice. Shayna, um, I didn't see you in a while. Everything all right? Like, in our classes, aren't they? I know seeing your message here.
I am surviving.
And now seeing your message here, right? Like, if you see my WhatsApp, it's
Yes,
just
sir.
bombarded with messages. So, like, I was scrolling, I see it just now.
Yes, sir.
You feeling any better at all?
A bit. We supposed to go back. Yeah.
You were supposed to go back by the doctor or something.
Mm-hmm. But
So,
it's not bad.
is it just a headache or is it more?
I hit my head and they say the trauma might have caused something, so I'm supposed to go back for a CT scan. No, jet.
Oh, damn. Like, how did you hit your head though?
It's on a rock.
A rock.
Yes.
Oh my. That is concerning. That is concerning. Don't tell your friends out there because I feel like if you say anything, your friends will be like, well, yeah, you hit your head on a rock. Don't tell your friends that. When I say right, you'll clown your face. You'll clown your
Yes.
face. I wouldn't clown your face, eh? I thinking maybe, no, I wouldn't do that. I wouldn't do it.
Yes.
But I hope you feel better soon. I hope nothing is wrong with your brain because
Yes.
your brain is a very important organ in your body.
Yes.
Right. So let me explain this formula from scratch. So Zachary, hence we understand that specific heat capacity is the amount of energy you would need to raise the temperature by 1 degree Celsius or 1 Kelvin for a kilogram of a substance. For a kilogram, right? For a kilogram.
Yes,
Yeah?
sir.
Okay. Now, by 1 Kelvin or 1 degree Celsius, that's the part that I should add in. All right? By 1 Kelvin or 1 degree Celsius. And let me just explain this quickly because I don't think in school your teacher is going to explain it very well. And when I was doing physics, this was a part I was confused about. I know a lot of people are confused by this. So, yeah. So, let me write back down the formula. So EH, or I could just simply write E for now. E is equal to mc delta T. Now, delta T is actually the change in temperature. So change in temperature. Now, the change in temperature is the same for Kelvin and Celsius, right? Same for Kelvin and degrees Celsius. And let me explain why. So, Karina, let's just say we had, let me use the same example, right? So, Karina, I'm going to use the same example. Karina, what's the change in temperature here? You start off at 30 and then
2
you end over at
degrees.
32. 2 degrees, right? Okay. So the change in temperature, we say that the change in temperature is equal to T2 minus T1. So where T2 is the final temperature and T1 is the initial temperature. So 32 degrees Celsius minus 2 degrees Celsius. Well, actually, delta T don't really have any units, right? So 32 minus 30, and that would just be equal to 2. All right. So, Karina, that was a degree Celsius. What if we converted these to Kelvin? Let's see what's going to happen. So, Karina, convert 30 degrees Celsius to Kelvin for me. I'd like you to do that for me. Convert 30 degrees Celsius to Kelvin. Karina,
Still
do you know how to,
disconnected.
Karina, do you know how to convert Celsius to Kelvin?
Yes.
All right. So how would I convert 30 degrees Celsius to Kelvin?
30 degrees at 273.
And what would that be?
That would be 303 Kelvin.
All right. 32 degrees Celsius is how much Kelvin? Let me get somebody else to try. Shina, what would 32 degrees Celsius be in Kelvin?
$305 Kelvin.
Okay. So Karina, what's saying Karina? So Shina, let's find delta T, right? For the same thing but in Kelvin this time. So what's T2 this time? What's T2 this time? If we use in Kelvin, 305, and that'll be minus what?
303.
What is 305 minus 303?
2.
So guys, does it matter if it's in Celsius or Kelvin?
No, sir.
No. Zachary, does it matter?
Nah, sir.
Because Zachary, are we still getting the same change in temperature?
Yep.
Yeah. So guys, don't let that confuse you. I know it confuses a lot of people. So if it's Celsius, if it's Kelvin, it doesn't matter. But both of them need to be in the same one though, right? So just add in or 1 degree Celsius to the definition. All right, I presume you all have that added in by now. So let's look at the formula from scratch. So E is equal to mc delta T. E stands for heat energy. That's what E stands for, heat energy. What are the units for energy, guys? What are the units for heat energy? Could somebody tell me what's the unit for heat energy? Somebody said joules?
Yeah.
All right. Then we have mass. This is the mass of substance. And what do we measure mass in physics?
Kilograms.
All right. Then we have C. What is C? Does anybody know what C is? Okay, everybody else quiet. So C is actually the specific heat capacity. It is the specific heat capacity. Right? And does anybody know the units for that? Zachary, do you know the units?
Nah, sir.
All right, let me show you a way to figure out the units, right? So could you remind me what specific heat capacity is?
Say the specific heat capacity
Mm-hmm.
Is the amount of heat required to change the temperature.
Later. So is the amount of heat energy. So what do we measure energy in?
Joules.
Right? So is the amount of heat energy, right? Continue.
Required to change the temperature of 1 kilogram of a substance by 1 Kelvin.
Yeah, so that's the units. So is the amount of heat energy required to change 1 kilogram of a substance by 1 degree Celsius or 1 degree Kelvin, or by 1 Kelvin. This is the units. Joules per kg Kelvin. So as you can see, is the amount of energy it would take to raise the temperature of 1 kg of a substance by 1 Kelvin or 1 degree Celsius. Understand?
Yes, sir.
All right. So that's the units. So try not to forget it. Try not to forget it, right? Right. Okay. Next thing we need to look at. Right? And let me just also wait. When you guys when I said to copy this down, did you all copy it down? Because look all the units right here.
Yes, sir.
So like let's suppose I know then. Right? And the units could also be joules per kg degree Celsius. Could also be that as well. Right? And what do you all think delta T stands for? We would have just gone through it. What do you think delta T stands for?
Change in temperature.
Change in temperature.
Right? Change in temperature. And we find that by subtracting what from what?
T1 from T2. I mean T2 from T1.
Well, it's actually T1 from T2. So T2 minus T1. I find that notation has always confused people. Like when you say from this, from that, just say T2 minus T1. That's the least confusing thing, right? So T2 minus T1. So if you didn't already, copy this down. Make sure you have what each one represents and you have the respective units. Please do that. Right, so do that one time. As soon as you have every single thing copied down, let me know. So Zachary, as soon as you have everything, you let me know, right?
Yes, I have everything.
Including the units as well and what each thing represents.
Mm-hmm.
All right, that's good. Karina, what about you? Do you have every single thing?
Yes, sir.
Okay. Jiran, do you have every single thing?
Yes, sir.
Okay. Shayna, what about you?
Yes, sir.
Okay, so I want to let you close all the books. I'm being real trusty here. I trust a lot. All right, what does C stand for?
Specific heat capacity.
And what is specific heat capacity?
The units that I was asking for.
Nah, asking you actually your weight is. What is specific heat capacity? Try to remember it without looking back.
So the amount of heat energy required to change 1 kilogram of a substance.
Right?
Remember, yes.
By
By
1 kg,
1
by
kg,
1,
1 degree Celsius.
right, right, 1 degree Celsius or 1 Kelvin, right? Make sure and put
Yes.
all as well, right? It'll show that you know a bit more than the average students, because some people, they don't know that it don't matter, right? So, and what are the units for specific heat capacity? Have two alternative forms, but what are the units?
I want to get something straight.
Joule/kg, Kelvin,
Or,
Yeah.
or Joule/kg, degrees Celsius.
great. So I believe now we could go ahead and do a question. But before I continue, this formula, right? Please understand something and write this in your book. Do not use this formula if there is a change in state. You're only going to use this formula for the period for which something just changing in temperature. Right? So do not use this formula if there is a change in state. Only use when there is an increase or decrease in temperature. All right, so please copy that down. If there's a change in state, you're going to use the formulas for latent heat of vaporization and latent heat of fusion. You're not going to use this formula. All right, and you could also copy down this as well. So specific heat right? So please know that as well. So as soon as you guys have this copy down, let me know. We could do a question.
Yes, Adam.
All right. As soon as the rest of you all have copied this down, let me know. Right. So Jadon, Karina, Sheena, let me
Yes,
know.
sir.
Right.
Boxes
Yes,
on.
sir.
All right. Cool. Our last class we look at an example, right? But that example was also containing latent heat. See if I get a question quickly. Okay, I'd like you all to try this question for me. Try part A. Give that a try. Now, guys, Remember, if your mass is in grams, you have to convert it to kg. Please remember that. Right, so I'm going to read the question. Yashoda prepares some lime juice on a hot day. She adds 80 grams of ice at a temperature of 0 degrees Celsius to 0.32 kg of lime juice. The temperature of the lime juice decreases from 29 degrees Celsius to 8 degrees Celsius and all the ice melts. Calculate the energy required to melt 80 grams of ice. Actually, I do think you guys will be able to answer that. You still need to know about latent heat of fusion to do that. Karina, maybe you might not be able to answer part A.
No, sir, because Jenny, when you sent that question in each chat, I was watching it and I wasn't confused, but I was like, what going on? I have the same book that you're using here for the questions, and I kind of went back to kind of check it out, but I didn't really understand as much.
Well, I can kind of give a little explanation about it, right?
Mhm.
So, Jalen, so
Yep.
she added ice into the lime juice, right? So,
Mhm.
initially, what's the temperature of the water of the lime juice? I mean,
The temperature of the lime juice, it was the water or the lime juice? But I don't know water. It was eight.
water and lime juice, same thing. Lime juice, 29, right?
Mhm.
And what was it after adding the ice?
Wasn't enough.
What was it?
That's not hold on. Gotta go back and sure.
8 degrees.
Right, 8 degrees Celsius. And what would have had to happen for this to occur? Let's think about it, right? So, wouldn't the ice would have had to turn to water?
Yeah.
All right, ice is at what temperature? What temperature is ice at?
0 degrees.
Right? So ice at 0 degrees Celsius would have to melt to what?
0 degrees.
Right? Water at 0 degrees Celsius. Oh, you understand that? So ice, so Jaden, remember last class I was kind of telling you that if you hold a block of ice in your hand, when the ice melts, that water, that's the molten ice, right? The water. Is that water cold or is that water warm?
It,
What you say, Jaden?
the moment you add it, it's warm.
Right. So like if you hold a block of ice on your hand, right? The water that you get from the ice, is the water cold or hot?
Cool.
Cool. So at the instantaneous point when ice melts and turns to water, the ice is 0 degrees Celsius and the water as well is 0 degrees Celsius. Right? So this is a multi-step question. So for this part over here, you would have to convert this from ice to water, and that would be a change in state. So you'd actually have to use E is equal to MLF here. Right? You'd actually have to use E is equal to MLF. But we didn't do that yet. So I don't suspect you'd know how to do that. But this is what's going on. So Jadon, you had a glass of lime juice, right? You put ice into the lime juice, right? That ice would turn from 0 degrees Celsius ice to 0 degrees Celsius water, and it would melt and become part of the lime juice. Understand?
Yeah.
All right. Next thing. Do you remember what the mass of the lime juice was alone? What was the mass of ice juice? I mean, what was the mass of lime juice alone by itself?
0.32 kg.
Right? And Jadon, what was the mass of the ice?
The mass of the ice was what just now? 80
80.
grams. Yeah.
Right. So, when she adds the ice to the water, what's the new mass? So remember that the mass of the lime juice is 0.32 kg. How would I convert 80 grams to kg?
You would
How much grams are in a kg?
1,000.
1,000, right? So if you want to go from 80 grams to kg, you'd have to divide by,
1,000.
right? So what's 80 divided by 1,000?
0.08.
0.08. So if the mass of the lime juice is 0.32 kg and the mass of the ice block is 0.08 kg, what will be the total mass now?
It would be so for 40 kg. 0.40 kg.
Right. So when we spin back around to doing this question, all of this will come in handy, right? It will. So I want you just to keep that in mind. I'll find an easier question for you all at the moment because I feel like this question a little too hard for you guys right now, at least. Right, Sheena, you didn't do this in school, so you wouldn't be able to answer this question. But Sheena, I know you're smart, so I say maybe I give it a crack. But I didn't know you hit your head with a rock. So I excuse you. I excuse you.
Yes, sir.
Valid crash out. Valid crash out. All right. Let me see if I can find an easier question for you all. Yeah, what? Let me just do latent heat. So we'll be able to answer a full question. Right? So all you know about specific heat capacity. Right? The energy is equal to mc delta T, and we use that when there's a change in temperature alone. Right? Cool. Presume we know that. Okay, the next thing you need to know about is heat capacity. Right? So Zachary, could you read heat capacity for me?
Heat capacity is defined as the amount of heat required to change the temperature of a body by 1 Kelvin.
And then we just add in something we think are gonna add in.
Or degrees Celsius.
Right. Are you seeing the word specific here?
No.
Remember, I tell you, anytime you see the word specific, that means you're looking out for mass, right? You're looking out for mass. So if you're not seeing specific, don't expect mass. So heat capacity is even simpler. It's just the energy you need to change the temperature by 1 degree Celsius or 1 Kelvin. That is easy to remember, right?
Yes.
Okay, cool. And the formula for that is just, okay, so heat capacity is denoted by a capital C. Right? And the units for heat capacity is just joules. It's just joules per Kelvin or joules per degree Celsius. Those are the units for heat capacity, right? So I'd like you all to copy down what heat capacity is as well as the formula for heat capacity. And additionally, copy this down. They could ask you what's the difference between heat capacity and specific heat capacity. So copy that down. As soon as you have that down, let me know. Right. Do you guys have everything on the screen copy down? Yeah or no? As soon as you do, let me know.
Almost.
Almost? All right.
Finish.
Okay, Jaden, what about you?
Yes, I just finished.
All right. Shayna, you?
Yes, sir.
Okay. Cool.
I don't.
All right. Nice. So guys, which one uses mass? Is it specific heat capacity or heat capacity?
Heat
Somebody tell me.
capacity.
Which one uses mass? Specific?
Heat capacity.
No, specific. Remember, specific heat capacity is the amount of energy you need to raise the temperature of 1 kg of a substance by 1 degree Celsius or 1 Kelvin. Specific strictly deals with 1 kg. What is the definition of a heat capacity, Sheena? Just heat capacity. What is the definition for heat capacity?
The amount of heat required to change the temperature of a body. Oh, okay.
Yeah, that's not what I mean.
And
Heat
yes.
capacity is just how much energy you need to change something by 1 degree Celsius or 1 Kelvin. There's no mention of mass there. All right. Could you tell me the units for specific heat capacity? Do you all remember the units for specific heat capacity?
Says G/kg.
No, that's for heat capacity. No. Yeah, I feel like you're mixing it up and you're leaving out some stuff. I want you to tell me back the definition for specific heat capacity and you get your answer.
Says
Somebody,
specific is G/kg Kelvin.
right, because enter the amount of energy you need to change the temperature of 1 kg of a substance by 1 Kelvin.
Mm-hmm.
Right, so you need to include the Kelvin or the degree Celsius in the answer, right? Right. What is the units for heat capacity then? Wait, Jadon, I want you to tell me what heat capacity is. Not specific, just regular heat capacity. Jadon?
There's like the amount of energy you need to raise the temperature or something. The amount of energy you need
To raise the temperature by 1 Kelvin
by 1
or
year.
1 degree Celsius, right? So, what's the units for energy, Jadon?
The unit for
Energy.
uh,
Wait, sir?
joules.
Joules, right? And the definition was literally the amount of energy, so joules, required to change the temperature by 1 degree Celsius or 1 Kelvin. So you can either put Kelvin or you can say joules per degree Celsius, right? So Jadon, energy is measured in joules. Temperature is measured in Kelvin or degree Celsius. Mass is measured in kg. Make sure you know them things, right?
Mm.
And what's the formula between specific heat capacity and regular heat capacity?
Um, Isn't that the Q equals to MC? I forget what the triangle means. Q equals to MC triangle T.
Okay, you're talking about the specific heat capacity formula. I'm talking about a formula that have heat capacity and specific heat capacity in it.
Mm,
Is there any formula that you guys know that has heat capacity and specific heat capacity in it? So heat capacity is denoted by a capital C and specific heat capacity is denoted by a common C. Is there any formula with capital C and common C in it? Zachary, do you know? Is there any formula that you might have copied down with capital C and common C in it?
So you copy down today?
Yeah, today. You might have copied it down like 1 minute ago.
the C equals to MC.
Right. Capital C is equal to MC. That's the formula, right? That has, right? Because capital C, that's heat capacity. This is heat capacity. And what's common C?
One C is the specific heat capacity.
And what is M?
Mass.
So let me blow all your mind for a bit, right? Let me blow all your mind. What's the units for heat capacity? Let me work in degrees Celsius for now. What's the units for heat capacity? Tell me. It's joules per?
Kilograms.
No. I want you to tell me what heat capacity means. What does heat capacity mean?
So heat capacity is the amount of heat required to change the temperature of a body by 1 Kelvin or 1 degree Celsius.
Right. So fix what you just told me. You just told me joules per kg.
It would be joules per Kelvin.
All right. Joules per Kelvin or joules per degree Celsius, right? Yeah. Right. So I'm going to use joules per degree Celsius for now. Right. That one is fine. Right. So far you're with me, right, Zachary?
Yes, sir.
Okay. What do we measure mass then? What's the units for mass?
Kilograms.
Right. What's the units for specific heat capacity?
So the specific heat capacity is joules per kilogram degree Celsius or Kelvin.
Right. Now, joules / degree Celsius, it really means joules over degree Celsius. Right? Now, joules per kg degree Celsius really means joules all over kg degree Celsius. Could anybody tell me what's going to happen here?
So the kilograms would cancel out itself.
Right. And what would we end up with?
You'll just get G over degree Celsius
Equals to?
equals to
Equals.
Degrees Celsius.
Right. Zachary, remember the kilograms cancel off, so you just remember joules per degree Celsius. So you see, and by doing this, we proved that the left-hand side was equal to the right-hand side.
well, yeah.
Yeah, so that's if that's you to prove the formula, this is how you would prove the formula, right? You would put the units for heat capacity and the units for specific heat capacity as well as the units for mass, right? And you would cancel it off and show that the left-hand side is equal to the right-hand side. But isn't that cool, Zachary? Like by doing this, and we saw that they were literally equal.
Yep.
Yeah, because remember, specific heat capacity takes mass into consideration. So by multiplying by mass, we get rid of the mass aspect, and so this would be equal to this, using this formula. That's how it works. Right. Okay, so you need to be able to test for specific heat capacity, right? And this is method 1 using a calorimeter. So, Karina, I'd like you to give this a read for me.
Testing for specific heat capacity. Method 1. Calorimeter. This setup is called a calorimeter, an
No,
apparatus,
calorimeter.
oh,
Calorimeter.
calorimeter,
Mm-hmm.
an apparatus used to measure specific heat capacity. The following must be known to calculate specific heat capacity: mass of the material, voltage and current, time.
Right? And let me explain this formula for a bit. So this formula says that power is equal to, now I stands for current, right? Power will be equal to current multiplied by the voltage. That's what the formula says. So I is current and V is voltage, right?
Yeah, I thought it said power equals 4.
Oh, what? What?
Yeah, in the,
No, no, no.
the Roman numbers, that's 4.
Yeah. I don't know what you mean, but no. I is current and V is voltage. It's a good thing I pause and go through that, boy. You know, you still be thinking it's 4. That's okay though. That's okay. You're learning. You might scared there, boy. Right? And it must contain time, right?
Yeah.
Right. And this is the combined formula. This formula is not E is equal to 4T, yeah? Right? That formula is energy. Energy is equal to, what does I stand for?
Current.
What does V stand for?
Voltage.
And Jadon, what does T stand for? Jadon, what does T stand for? Can I hear in Jadon? Somebody else. What does T stand for? What do you all think?
Time.
T stands for time, right? T stands for time. So when you're trying to figure out the specific heat capacity using a calorimeter, you need to know the mass, you need to know the voltage and the current, and you need to know time. Additionally, you would need to know these specific formulas. You would need to know that P is equal to IV, and you need to know that E is equal to IVT. Right? Cool. So I think I should copy this down. Yeah, I should copy this down. They do ask this in physics. They ask you, what is the experimental setup to test for the specific heat capacity? And if they do that, they will give you they will put on the diagram and they will ask you to figure out the specific heat capacity. Right? So copy this down, and the title is Testing for Specific Heat Capacity, Method 1, Calorimeter. Zachary, did you ever learn these formulas before? P is equal to IV and E is equal to IVT?
Awesome.
No? Okay. Shayna, what about you? Did you ever learn these formulas before? P is equal to IV and E is equal to IVT?
We I knew power, not energy, but we didn't really do it.
Okay, so
Yeah.
Shayna, did you finish this topic in school or not? Huh?
We did a part of it, but I wasn't supposed to do it for the term. Didn't make a mistake, so we didn't finish it.
Okay. In my head, it's like, no matter when you learn this thing, you still need to know it for the exam. So it's like, best you just learn it anyways, honestly. And no matter when you learn it, you just have to learn it for the exam.
Yes, we are done.
Okay, cool. What about the rest of you guys? Now, just because somebody said they finished, that doesn't mean you ought to say you finished too. If you need more time, tell me. Or I need more time, or let me know what's going on.
No, sir.
You finished?
Things first.
Yeah.
What about the rest of you guys?
And the last part.
Yes, sir.
Last part? Okay.
Okay, then.
Okay. So let's look at, so we are going to actually do this question together. Let me just erase the answer quickly. So who wants to help me with the question? Do we have any brave volunteers? Any brave volunteers? I don't know how to be scared and we learning. Any brave volunteers? Anybody? I'll leave them hanging, boy. Ways, boy. Anybody at all? Zachary, you feeling shy or you're like,
That's
it was like, I thought you say let me go. No, no,
Nice. Let me do it soon.
all right, get the question I read from her.
The metal aluminum block is heated for 3 minutes with five. See what you mean?
A means amps.
Right.
And okay, let me just write down something to the side, right? So remember how I said we needed mass of new material, voltage and current and time?
Mm-hmm.
So voltage is measured in V. Current is denoted by the symbol I and it's measured in A. Yeah. So you need to be familiar with that. And the main formulas we're going to use is P is equal to IV. And what was the other one? What's the other one you need to know?
E is equal to IVT.
Right. And you may need to know another one. Was the other formula you learned? E is equal to what? There was another formula you learned. E is equal to
MC squared.
nah. E is equal to MC what?
Delta temperature.
Yes. E is equal to MC delta T.
Okay.
Right? Sometimes you would see Q is equal to MC delta T. They mean the same thing. Same thing. Right? So let me get into it, right? So Zachary, read the question again.
The metal aluminum block is heated for 3 minutes with a 5 amp 10 voltage supply. If the initial and final temperatures of the 2 kilogram block are 30 degrees Celsius and 35 degrees Celsius, respectively, calculate its specific heat capacity.
Okay. So, let's think. All right. All right. So, they're telling us at the time. So let's write it down. They're telling us at T. Why is that happening? That's really weird. 1 second. Okay, cool. Yeah, so they're telling us that the time is 3 minutes. Now, Zachary, in physics, do we work with time in minutes?
This is seconds.
So how would I convert 3 minutes to seconds?
3 by 60.
What's 3 by 60?
180.
Right, they're telling us that the current I is equal to 5 amps. They're telling us that the voltage is equal to 10 volts. They're telling us that the mass is equal to 2 kg. They're telling us that the initial temperature, so they're telling us that T1, what's T1 equal to? What is T1 equal to? Right, 30 degrees Celsius. What is T2 equal to?
35 degrees Celsius.
And we could find the change in temperature one time.
Yep.
What's the change in temperature?
5 degrees Celsius.
Right, that's just T2 minus T1. So here what? Let me just solve from our side. The first thing we should probably calculate is the power. Power, right? Actually, you could just use the combined formula. Unless you want to do extra work. So we know that E is equal to IVT. And if you know that, E is equal to IVT. So tell me, what is, we're going to do some substitution now. So what is the current? What's the current?
E is equal to 5 by 10 by 180.
5 by 10 by 180, yes. So calculate the energy for me.
9,000 joules.
Right, so that's the energy, 9,000 joules. So in other words, right, Zachary, we are supplying 9,000 joules of energy to the, all right, so wait, right, so we had the metal block, the lagging, the heater. So we are supplying that to the thermometer. I don't know if you understand that.
Yep.
We are supplying that to the thermometer and the metal block. So do you understand that we have a heater here? The heater is going to get hot and it's going to radiate heat to the thermometer and the metal block. So the temperature of the metal block is what's changing. Do you understand that?
Yes, sir.
And we are trying to figure out the specific heat capacity of the metal block. So we have the temperature here. We have the thermometer here. So the thermometer is here to measure the change in temperature of the metal block. And the metal block is actually what's getting heated. So we know the energy that is going to the metal block is 9,000 joules. Yeah. All right. We want to figure out the specific heat capacity. Tell me, what is the symbol for specific heat capacity?
C.
Common, C, right? Is there any formula that you know that has E is equal? I can't see it. Is there any formula that you know that have a common C in it?
Yes.
What formula is that?
Heat capacity.
What's the formula for heat? No, specific. Use specific.
What?
Is use specific heat capacity formula. What is the specific heat capacity formula?
As E is equal to MC changing T.
Now you're going to say you was going to say use C is equal to MC, but let me show you why that would not work. For you to be able to solve for unknown, you need one unknown in the entire equation.
Mm-hmm.
Tell me this, right? We know what the mass is, yeah?
Yeah.
Do we know what the heat capacity is?
No.
Do we know what the specific heat capacity is?
No.
No. So think about it. We just now find for E. So chances are we're looking for a formula that have E in it, and we're looking for a formula with specific heat capacity in it. So that's why this one should have come to mind. You can't use this one because there's two unknowns. Right. So let's observe. Thelma, do we have E?
Yes, sir.
Do we have the mass?
Yep.
Do we have C?
No.
Trying to find for it though. Do we have delta T?
Yes, sir.
So how much unknowns we have?
1.
If you have one unknown, can you proceed to solve it?
Yes, sir.
Right, so if I want to make C the subject of the formula here, what would I divide by on both sides?
You divide by the change in T and M.
Correct. So guys, if I want to make C the subject of the formula, I would need to divide both sides by M delta T. And if you are wondering why, well, if you're trying to make something the subject of the formula, then you want that to be the only thing on whatever side it's on. So the M's are going to cancel off, and the delta T is going to cancel off, and that would leave us with C. So in other words, tell me, C is equal to what?
C is equal to E over M delta T.
Right. So from here, we just have to substitute, and we'll get our specific heat capacity for the metal block. What is the energy we're supplying to the metal block?
9,000 joules.
What is the mass of the metal block?
2 kilograms.
And how much did we change the temperature by?
5 degrees Celsius.
Right. So if you work this out, you're going to get that the specific heat capacity is?
900
Right.
G.
And nah, do you have more units? It's 900 J per?
900 J slash kg degrees Celsius.
Right. Did you all understand how I work this question out?
Yes.
All right, so let's run through it one more time. So we had a metal aluminum block, right? So as you can see, we have a heater over here. Now, the heater is inside the metal block. So Karina, if you have a heater here and it's inside the metal block, what's going to happen to the metal block?
So can you repeat?
So Karina, we're just going over the whole problem now, right? So Karina, if you have a heater that's inside of a metal block, what's going to happen to the metal block?
It's going to start getting heated.
The temperature of the metal block is going to increase, right? Yeah?
Yeah.
Why do you think I have a thermometer in the metal block?
To measure the temperature it rises to.
Great. So, this is the logic behind this question, right, Karina? We need to figure out the energy that we are supplying to the heater because that's the energy that the metal block is going to receive. Do you understand that?
Yeah.
Do you understand? So can you understand that the metal block is going to receive the heat from the heater?
Yeah.
And heat is a form of energy, right? So we want to find for E, correct?
Yeah.
Good. So we use the formula E is equal to IVT to figure out the energy that the metal block would receive from the heater. And we found it to be 9,000 joules. Right? You okay with that?
Yes, sir.
Okay. So Karina, we know that the metal block is going to receive 9,000 joules of energy. So we use the formula E is equal to mc delta T to find for specific heat capacity. So if we want to find for specific heat capacity, we divided both sides by m delta T. Why do you think we do that?
I didn't quite hear you.
Did this part confuse you? Be honest with me, like real honest. Did this part confuse you? You understand that I divide by m delta T, so it'll cancel off to leave more with C?
Yeah.
And we want to find for C, specific heat capacity of the metal block.
Yeah.
So we want to find for C. So we end up with C being E over m delta T, right? So E is 9,000 joules, the mass is 2 kg, and the change in temperature, we saw that the change in temperature was from 30 to 35, so that's 5 degrees Celsius, right? So we end up with 900 joules per kg degrees Celsius. I mean, if you understand how we did the question.
So I understand.
Yeah, sure.
Yeah.
What about the rest of you guys? Jayden, is there anything you want me to go over in detail?
So you could just go over like the last like 5 minutes. I had meant to pick up those because we're talking.
Okay.
Yeah.
That a little, I can't do that all the time, because
Well, all right. No, I
I
understand.
can't.
Understand.
No, but I'll explain it this time because this is an important concept to understand. But I can't do that all the time. All right.
Yeah.
It have the recordings, right? And you could always ask me after class, but
True.
it's a little unfair to all the other students that was here and was paying attention the whole time. If you understand what I mean.
No, that's it. I understand. Yeah.
So I'll go it over one more time, right?
Mhm.
Shayna, do you understand the question?
Yes, sir.
All right. So one more time, right? So, Jayden, if you have a heater in a metal block, what's gonna happen to the metal block?
It's gonna get heated. Like it's gonna take the heat. It's gonna get
Right.
hotter.
So the energy, it's gonna get energy from the heater, right? The heater is gonna give the metal block energy. That makes sense?
Yeah.
Right. So the first thing we would need to do is we would need to figure out the energy supplied by the heater. You understand? That's the first part. Because that energy is the energy that the metal block is going to receive. Do you understand that?
Yeah.
Yeah, sure. All right. So to find the energy of the heater, we use the formula E is equal to IVT. So they gave us I to be 5 amps, they gave us voltage to be 10 volts, and we found the time to be 180 seconds. Initially, they had given us the time as 3 minutes, but you have to convert minutes to seconds, so you multiply that by 60. So the time is 180. So when you multiply this out, you're going to get 9,000 joules, right? So Jayden, you see this heater over here? You see the heater?
Yeah.
The heater is going to provide the metal block with 9,000 joules of heat energy. You understand? So that 9,000 joules of energy is going to heat up the metal block now. So the next formula we're going to use is E is equal to mc delta T. And how do I know to use this? I'm going to use this formula because, watch, I just found the formula I just found what energy was. Jayden, we know that the metal block is going to receive how much energy?
9,000.
Right. So the next formula that I would want to use is a formula that has energy in it, right? So we use this formula here. E is equal to mc delta T. E, what does E stand for again?
Energy.
What does M stand for again?
Mass.
What does C stand for again?
Um. Um.
Right here.
Specific heat.
Right. C stands for specific heat capacity. And that's actually what they want us to figure out, right, Jayden? They actually want us to find for the specific heat capacity, common C. Do you remember what delta T stands for?
No.
Delta T is a change in temperature. Change in temperature. So at the start, it was 30 degrees Celsius, and after heating, it was 35 degrees Celsius. So what do you think the change in temperature was?
5 degrees. Okay.
Right. So delta T was 5 degrees Celsius. Right. So Jadon, we know what the energy is. Energy is 9,000. We know that the mass is 2 kg. And we know that the change in temperature was 5. What's the only thing missing?
The specific heat capacity.
Right. The specific heat capacity is the only thing that's missing here. So I'm going to divide both sides by m delta T. And why am I doing that? I'm doing that so the m is going to cancel off and delta T is going to cancel off. What does that leave us with on the right-hand side?
Leave us around C.
Right, because we're trying to find for C. We need C to be the only thing. If I do it on one side, I need to do it on the other side. And then I just flip it around. So C is equal to E over M delta T. Let me know if you understand that. Do you?
Yeah.
So I divide
Yeah.
both sides by M delta T. All right. And the next step was just substitution. So we know E is 9,000. We know M is 2. We know delta T is 5. And about 900. That's it.
Okay. I understand.
Okay,
Thank you.
cool. No problem. Zachary, do you feel confident in this question? This is a question that they could very well bring in the exam.
Yes, sir.
All right. So Zachary, let us annotate the diagram. So how much energy is the heater providing?
9,000 joules.
Right, providing 9,000 joules. And how could it do that? Let's see. It could do that because what's the voltage? What's the voltage across the heater? Remind me?
So it was 10 V.
10 volts, right? And what was the current flowing through the circuit?
It was 5.
It was 5 amps. And what was the time for which it was on?
180 seconds.
Right. Now, you see that formula to come up with? E is equal to IVT. That formula comes from P is equal to energy over time. That's where that formula comes from. And remember, power is equal to I by V. So if you do a substitution, you'll see that IV is equal to E over T. And if you make E the subject, what would you do? What would you do, Zachary?
Multiply by T.
And where you go?
E is equal to IVT.
Yes, that's how they got that formula, right? Instead of doing the derivation in the exam, right? So, but this is what's happening. You have a voltage across the circuit and you have a current flowing. And that power is being supplied to the heater, right? It was on for 180 seconds. So in that time, it provided 9,000 joules. We're on the same page?
Yes, sir.
Right. And that heat would go to the metal block now. So does that make sense?
Yep.
Cool. Right. So metal block, it receives 9,000 joules of heat energy. Right? And what change in temperature did the thermometer read?
5 degrees Celsius.
Right. So the metal block is going to heat up, right? It's going to heat up from 30 degrees Celsius to 35 degrees Celsius. So do you understand 100% why you would then use E is equal to MC delta T?
Yes, sir.
Because the metal block is receiving the energy. So we know what E is, we know what the mass is, we don't know what the specific heat capacity is, so we can solve it. And we know that the change in temperature is 5. So everything is 100% clear. Like, you have no doubts at all. Yeah, like this makes...
Yes, sir.
Okay. Karina, you understand everything?
Yes, sir.
Okay, good. So the question could come like this, or the question could ask you to describe the experimental setup for testing specific heat capacity, and you would have to draw this diagram. Yeah, and you would have to say it's a calorimeter, right? Question: why do you all think it's called a calorimeter? Karina, what are calories? And you
Mark,
know what? Say that again.
a marks?
No, calories is energy.
I didn't know that.
Yeah, calories is energy. So they call it a calorimeter because you're measuring the energy. Calorimeter. Did any of you all know that calories is equate to energy? Any of you know that? Um, Zachary, did you know that calories is actually a unit of energy?
Awesome.
Yeah, so like when all you see energy drinks, look at the calories. Calorie value, you know that. But now you know, right? Calories is actually, like if you look it up online, it's literally a unit of energy. It tells you how much energy there is in our food. So, Karina, now you're gonna know, right? So, Karina, if you're like real hungry and you're low on energy, will you now look for something that's high on calories or low on calories?
And the drugs.
High in calories.
Yeah. Shayna, did you know that before? That calories equates to energy?
No, sir.
What? Okay, okay. Who else? Jalen, did you know that? That calories is equate to energy?
Did not.
Did you know that calories equates to energy?
Okay, I did not know that.
So if you look at the caloric content for a food or like a snack or something, the calories is the amount of energies. I mean, is the amount of energy that food or dessert would give you. Now, if it's too much energy and your body doesn't utilize it, it gets stored as fat. That's the whole concept. Yeah.
Mm-hmm.
So that's why when people on diets and they're not consuming much calories, they get tired because their body don't have enough energy. The more you know, the more you know. All right, method 2, method of mixtures. So Jadon, to make sure I have your attention and you're not doing anything, I want you to help me here. I want to make sure you're locked in and you're focused.
Mm-hmm.
So read this for me.
Since the specific heat capacity of pure water is already known as 4200 joules or kgK or 4.2 joules, this value could be used to determine the SHC of another
Wait.
material.
What do you think SHC means?
I'm not sure.
Nah, that's not good enough. You could figure it out. I'm sure you could figure that out. Jadon,
Mm.
you could figure that out. Come on.
Is it
It could,
something we wrote down already?
yes. SHC.
Oh, specific heat capacity.
You see? You see? So like when you say you don't know something,
Mm-hmm.
it is gonna prevent you from figuring it out. So like now that you figure it out, I'm sure you would forget it less frequently because
Yes.
you actually figure it out. If I did just tell you what it was like, you would not learn anything from that. But you see, like you figure it out. That's how learning this happen. So you know SEC specific heat capacity. Cool. All right. So I read it back one more time. So since the specific heat capacity of pure water is already known as 4200 joules per kg Kelvin, I'm going to cross off this one because truth be told, we never really use this one. Like I've never seen in my entire life, and as somebody that has done tertiary level physics, I never see this in my life. We don't ever use 4.2 joules. Never. This is never use that one. We just always use this one. Right? Jadon, you think you could figure out why we just mainly use this one? Look at the units. Look at the units and see if you could figure it out. Was
Yes,
he?
you don't use grams with the
Ex-
formulas.
Exactly. See, you're using your brain, figuring it out. Big up yourself, right? That's good. We just never use grams. We use kg. Or we use kg. Good. So since the specific heat capacity of pure water is known to be 4,200 joules per kg Kelvin, this value could be used to determine the specific heat capacity of another material. The principle to remember is, right? So read this from Majida and tell me if it makes sense.
Heat gained by water equals to heat lost by metal.
Think about that for a moment. If something gets hot, doesn't that mean it's taking the heat away from something?
Yeah.
Think about into electronics and car audio and thing.
Not so much.
Not so much. Yes, game and thing.
Yeah.
You have like a gaming PC or something, or
A regular laptop, but I understand the basics of it. It
all right.
basically by this statement, is it just saying that like the metal initially would have a certain amount of heat, and in the water it would be just be pulling. No, yeah, the water would be pulling that heat away from the metal to keep it cool. Basically, that's what it means.
Yep, that's a perfect explanation. I couldn't explain it better myself. So you have
Okay.
it, right? An example would be like a heat sink on an IC, a heat sink on like the CPU of a gaming laptop or something. So like the metal would extract the heat and pull it away from the CPU. In this case, the water would take the heat away from the metal, just like you said, right? So read this part for me now.
By measuring the initial and final temperatures of both the water and metal, the following formula can be used. MC delta T water equals to MC delta T substance.
Right, and let's try to understand why. Isn't heat a form of energy?
Yes.
So we are saying that the energy gained by the water is equal to the energy lost by the metal. Remember, E is equal to MC delta T. So what we're saying is the energy gained by the water is equal to the energy lost by the substance. Does that make sense?
Yeah.
All right. Zachary, does that make sense to you?
Yes, sir.
So like Zachary, if the water gaining heat, how are we gaining heat? Like look at this. So we have water here, right? This setup is a bit different than I remember it being. But let me explain how it go work, right? So Zachary, imagine you heat up a metal block, right? And then you drop it in a beaker of water or something. What would happen? You tell me. If I heat up a metal block and I drop it in a beaker of water, what would happen?
The metal block would lose the heat because it would be the water, since it's cooler, it would pull the heat from the metal block.
Right. So would you say that the metal block gains energy or it loses energy?
Loses energy.
Right? But that energy it loses goes to where? Where does that energy go?
To the water.
Exactly. So do you understand why we're saying do you understand why we're saying the energy? So is the energy lost by metal block? That would be equal to what?
So repeat that.
So the energy lost by the metal block would be equal to what? What do you think?
Energy gained by the water.
That makes perfect sense, right?
Yeah.
Yeah. Because Jadon, do you understand that if you heat up a metal block and you drop it in a beaker of water, and you could understand that the energy would leave the metal block and it would be absorbed by the water?
Mm-hmm.
Good.
That was like those
Right?
random videos where people would just heat up like a metal
Yes.
ball, just drop it in the water, and you'll see the water start to bubble.
That self. Like it had like the 1,000-degree ball challenge or something where like
Yeah.
just heating up a bunch of balls and dropping it on different things. Yeah.
Yeah, 2018 was random for that.
Yeah. Right. So that's why we're saying M So MC delta T will be equal to MC delta T. Because we know E is equal to MC delta T. Karina, let me know if you're lost. Karina and Shina, let me know if you're lost.
No, sir.
Karina, are you lost?
No, sir.
Alright, so Karina, do you understand that if you take something hot and you put it in water, would it remain hot or would it lose the heat?
It'll lose the heat,
And what would gain that heat?
the water.
Perfect. So I say energy lost by the metal block is equal to energy gained by the water. That's the whole concept behind the method of mixtures. Right. So let's look at our question now. We're gonna figure this out by ourselves because we bad like that. Jaden, and we bad like that. Bad like Cravent.
Not like that, yeah.
Yeah. Zachary, we badent.
Of course.
Well, let me try to figure this out then. And I'll let you do example 2 by yourself. So, Jaden, you help me with the first question. Give the question I read.
Example question: a 50-gram block is placed in 200 grams of water. The block was heated to 100 degrees Celsius. The temperature of the block dropped to 30 degrees Celsius, and the water rose from 30 degrees Celsius to 35 degrees Celsius. Using, well, 4,200 joules
No,
kilograms.
well, in this question, they say to use the 4.2. If
You
in
have to use
physics,
it.
yeah, if in physics they say you had to use something, you can't just use something else. So we got how to use that, right? Yeah, continue.
Well, okay. 4.2G slash GK as the SHC of water.
Wait,
Calculate the
what does SHC mean? What does SHC mean again?
specific heat capacity.
Right. Yeah, continue.
Calculate the SHC of the block in joules slash GK.
Okay, so based on the units, based on the specific heat capacity of water they gave us, and by them saying this, right? Do we have to convert anything?
No, you don't.
No, because we already have everything in
In
grams and
grams, yeah.
yeah.
Sir, and you have to change the degrees Celsius to Kelvin.
You actually don't. For these kind of questions, you don't. And let me explain why, Karina. Karina, watch this carefully, right? I would have did an explanation here. Check this out, right, Karina? Remember we doing this question? Remember we did this? Check this out.
Yeah.
So tell me, Karina, the change in temperature for degrees Celsius, it was 2. And what was the change in temperature for Kelvin?
Was also 2.
Exactly. So it doesn't matter for this particular thing. When we look at gas laws, it will matter. But when you're doing specific heat capacity, it doesn't really matter much.
Oh, so I probably mixed them up.
Probably. But like when I was in CSEC physics, right? I was always wondering, does it matter? But now that I hear, I can tell you don't matter. Right? It doesn't matter, guys. It only matters if it is gas laws. Like all you see the it's a let me show you something. Like all you see the like this is the thermal physics as we doing now. Where yeah, so like even like in this level, you still use formulas I did in CSEC physics. So like if all you want to do engineering, right? Please make sure you're good with CSEC physics because they will come back to bite you. Because there's like the same things over and over and over. Honestly. I promise, like if you want to do engineering, please make sure you grasp CSEC, like everything at the CSEC level. Please don't put yourself through that torture. You know, if you're not good with CSEC physics, go do engineering. Any other looking to be engineers? Zachary, you looking to be an engineer?
Awesome.
Nah. Um, Karina, what about you? You looking to be an engineer?
Yeah, I'm not even sure what I'm doing yet, but it always did cross my mind.
Okay, I see. Well, if you want to do engineering, make sure all of this stuff you're real good in it. Like you're real good in it. Cause like when you go UE or university, they don't explain anything to you. They assume you know it. Just saying. So like you see what taking my time here? Nah. In UE they just speed run things. They go finish this whole topic in one class in like an hour. It's
So
crazy.
you think we could do lessons in UE?
I want to, but I would mainly teach electrical engineering courses because I do electrical. Yeah, I wouldn't really. I'll teach maths. That's the only thing I really teach, right? So,
I
Jadon, let me answer
feel
this
like that
question,
could
right?
be a good start of business.
That'd be a good what?
Start of business.
It would be a good business, you know. I would think about it when I get time. So, Jadon, let me answer this question. So, Jadon, just remind me, if you place a hot block in water, what happens to the block?
Cool on the water or any heat.
Right. So, we saying that the energy, mc delta T of the water, would be
Mm-hmm.
equal to the energy mc delta T of the, in this case, the
Substance.
block, right?
Okay.
Right. What is the mass of the water?
The mass of the water 200 grams.
What is the specific heat capacity of water? What did they give us for these? What did they give us here for the
The,
specific heat capacity of the water?
the water rose, well, 30 degrees Celsius.
No, that's temperature. We're talking about specific heat capacity. C. What did they tell us the specific heat capacity of water is? Look at the question, you have it. You could figure this out.
50 grams per space. 100 degrees Celsius. Temperature of the block dropped to 30 degrees Celsius and the water rose from 30 degrees Celsius to 35 degrees. So is it what, the 35?
No, that's temperature. That's not the specific heat capacity. Keep reading. Keep reading. Keep
The
reading.
35 using the formula as HHC of water. So you have to use the formula to figure it out. So the
No,
4.2,
no, that's not a formula. That's a constant.
okay.
This is not a formula, eh? A formula would have variables in it. This is just units. This is our number, 4.2. So like they are telling us that the specific heat capacity of water is 4.2 joules per grams Kelvin. So we had to use that, right?
Mhm.
You okay? Yeah, sure you're okay.
Yeah.
You can't take any word for it, you know. All right. And so we're gonna use C as 4.2. You okay with that?
Yeah.
What was the change in temperature for the water? Let's look. So what was the initial temperature of the water?
30 degrees Celsius,
Right? And from 30 degrees went to.
35 Celsius,
So what was the change in temperature there?
5 degrees Celsius.
Right. So this will be T1 and this will be T2. So delta T is just T2 minus T1. So that would be equal to 35 minus 30, which is equal to 5 degrees Celsius. So delta T is 5. Karina, do you understand that if I had converted this to Kelvin and I had converted this to Kelvin and I subtract it, I would still get 5?
Yeah.
Yes, it don't matter. It don't matter. It don't matter. Right? I make a note about that here. For delta T, it doesn't matter if the temperature is in Kelvin or degrees Celsius. Please note that. Right. Yeah. Continue. Jadon. Where's the mass of the metal block now?
The mass is 50 grams.
So I'm gonna put a 50 over here. What next? What to put next? Do we know what the C value is for the block?
No.
They actually want me to find that, right? They said
Yeah.
calculate the specific heat
Calculate.
capacity of the block.
Yes.
So we're gonna write C again. And do you know what the change in temperature of the block was?
5 degrees Celsius.
No, that was for the water.
Oh.
So read back the question.
Oh, it was 100 degrees Celsius minus 30
So what's the change in that
So
temperature?
70 degrees Celsius.
Right. Okay, so what do we have to find for now?
The C.
What we had to find for?
C is specific heat capacity.
Right.
So you'd
So
have
let's
to cancel it on both sides.
But before we do that though, we could simplify things, right? So what's
Uh-huh.
200 by 4.2 by 5?
4,200.
What you get for this?
4,200.
Okay, that's correct. Because 200 by 5 is 1,000, right? Yeah. 4,200, and that'll be equal to 50 by 70. What's 50 by 70?
That's what's that? 3,500.
Right? What next?
Well, you could cancel out the formulas on both sides. So you could
Nah, that's not formulas. The expressions.
expressions.
So these better yet just say terms. These are terms. These are terms. Right? So we want to find for C. So what do you think I should do on both sides?
Cancel it out on both sides. Or
What
you
am I
just
canceling out? What am I canceling out though? If I want to find for C, what should I cancel off?
C.
No, I'm trying to find for C. So C should be the only thing on that side. C should be the only thing on this side.
Mm-hmm.
What am I multiplying by C here?
3,500.
What would I need to do to get rid of the 3,500 by the C?
You divide it by 3,500.
Right. You're not getting rid of C, eh? You're getting rid of the number in front of
The
C.
number. Okay.
So the 3,500 and the 3,500 would cancel off. Right? Well, it's 4,200 over 3,500.
What, 1.2?
You get 1.2?
Yep.
Right? And that'll be equal to C. You need to put the units, right? So that'll be 1.2. And they told us the units would be joules per gram Kelvin. That's what they want us to use. Now, guys, it don't matter. Eh? Like, Shin, what's saying? Karina, in case you're confused, right? Like, okay, we work with Celsius, but here I was saying, Karina, it doesn't matter if you work in Celsius or Kelvin, right? The change in temperature is the same. So in the end now, you could say joules per gram Kelvin. It don't matter. It don't matter. It wouldn't matter, right?
Okay.
You understand? Because watch, the change in temperature will be the same either way. And you understand that?
Yeah, I understand.
Okay. And then that'll be equal to C. So now, Jadon, if you want, you can switch that around. So you could say C is equal to 1.2 joules per gram Kelvin. You understand?
Yeah.
And this is the method of mixtures. I'm gonna give you all one to do for me, like quickly. I'll time in only 3 minutes for this one. All right, go. Start now.
So hold on, my mother call him to do something quick.
All right. All right. So the time is up. Zachary, were you able to get through?
Exactly. He said, "Oh, his mom calling him to do something."
Oh, okay, okay.
I kind of still looking at him. So,
Wait, Jaden, as you talking it?
yes.
Oh, that's Zachary. Finish.
No, I was just no that he was the one that said his mom called him to do something. So,
Oh, okay, okay, okay. Yeah. Jaden, what about you? Are you getting through?
yeah, I yeah. Just give me like a couple seconds.
Could you tell me what the change in temperature was for the water?
The change in temperature for the water, it was 1.4 Celsius.
1.4, right? And what was the change in temperature for the iron?
The iron, um, I didn't get a.
Right. So what was
Oh,
the
no,
original
no, no,
temperature?
no. Hold on. It was 100, and then you minus in that by 19.6,
Yep.
80.4.
Yeah, that's correct. Karina, you getting through?
I think so, sir. Like I halfway through it so far.
Okay, what did you get for the change in temperature for the water?
The change in temperature, I got 1.4.
And for the change in temperature in the ion?
I got 80.4.
Yeah. Okay, good.
So I'm done. But to live from now that my brother had his fun time with my phone and mashed it up, but I don't mind going through it on the board with you.
What?
Yeah. So my week has been lovely.
Your brother older or
Yeah.
smaller?
Younger, he's 6. Yeah.
So you're gonna get a new phone soon, or like we're using right now?
Hopefully for Christmas. Oh, I'll leave it off my laptop. Oh my goodness.
Oh my god, you're really going through it, boy. First being hit by a rock, and then
There's something against her.
I will say our prayers fail. Somebody walk out over here.
Yes, but I don't mind.
Somebody.
I know, right? I don't mind going through it on the board. I finish, but I just
Okay,
wanted to let you know.
we'll go through it
So-
on the board, but really, right now you're like Ian Allen. Yeah, I really going through it. I don't know, you know the game. Right now that is you.
Yes. Oh my goodness.
All right. So I'm going to do the question on the screen with Shayna. Rest of you all, son. I don't care what you reach. Listen, my picture. I want to see that you're doing something. I want to see that you give it an attempt. All right, guys. Send me a screenshot of all they have so far. What's the screenshot of my picture? I want to see what you guys have so far.
Hey, is it possible to get like 0 points number?
Yep, that's fine.
Okay,
What did you get?
0.45.
Yeah, that's correct. That's correct. Big up you. Big up you. That's it. So let me run through the correction on the screen now. Right?
So I sent it.
Did anybody else get 0.45?
Yeah.
Yeah? Okay. Nice. Let me see what you guys have for me.
So me too.
Nice job, Jadon. I like that working. That's good working. That's working. That would give you a full marks. One thing though, you need to put your units for C. I need to
Yeah.
switch that down. So
I know, like, mm,
your units will be joules / gram Kelvin. Right? So Shayna, let's run through the question, right? So you would say MC delta T for the water is equal to MC delta T for the ion, right?
Yes. Sir.
What's next?
We're going through the equation. So 132 multiplied by 4.2 multiplied by the change in temperature, which was 1.4.
Right? And that'll be equal to
Is equal to 21.5 times C times the change in temperature for iron, which is 80.4.
right. Nice.
Right. And for water, you'll get 776.16.
776 point.
16.
And that'll be equal to
1728.6 C.
right. What next?
And then C will be equal to 776.16 over 1728.6, which will give you 0.45 joules over grams.
Right, joules per gram Kelvin.
Yes.
Yeah, good job. I could see that the rock didn't do damage. That's good. Yeah, you still have it. You still have it. You're still good. How that even happen though? Like, I'm curious. Like, he was walking or something. Shayna, he was like walking or something, and like, or like somebody pelted.
Okay. Let's just say I did not sleep the night before, so I was a bit out of it. It was during exams, and I happened to fall hit my head. That was the events.
What? So it was
I
right
was
in your.
I was no, it was the evening after exam, and I didn't sleep like for like 2 nights before that. And I feel like I was out of it, and so
You
yeah,
faint away and you hit your head or something.
I fell and I hit my head.
Really hell.
Yeah.
You know that maybe one day that'll happen to me, and we'll be able to be really like I will relate to. One day that'll happen to me. We'll be
Hopefully
twins.
not.
Something that happened to me once, right? Like I just so I have ADHD. So when I was small, used to have to go to like special lessons, and so like right after that, I walk in and I walk straight into AC, and I hit my head against the edge, the vertex of
Oh
the
my.
AC, and like my head started bleed and thing like dog.
Oh no.
I guess we are kind of twins, you know. Like, did your head start to bleed?
That's how to become a teacher, guys.
Oh,
So it gave all like some kind of
After
super
he hit
thinking,
his head, he
oh,
superpowers.
became
oh,
smarter.
the Karina,
Yeah.
Karina. That's it. Become a teacher.
Yeah, it gave all like some kind of like super thinking, like superpowers or something.
You know, like not have the average brain again.
Yeah, I have to go knock my head on something now because you see, two of y'all are proof. So
Yeah.
I need to find a rock
Oh.
or something.
Hey, oh my god. Hey, Zachary, you planning to hit the head?
The way you said it.
I said, you planning to hit your head too? I don't know if you know it was here any conversation, but apparently everybody in class want thinking to go hit their head to become like Shayna and myself.
Yes.
Just now Shina go be a teacher too. You know,
Yeah,
have the abilities.
Oh my.
but that's only first time I hit my head. Like when I was small, I climbed up on this table to help my mom, and like the table, it like the legs was unstable and it like slide on a fall and I hit my head and I had to go in the hospital. it's like
Well,
it's
so
like
you have twice the ability.
It have to
so
happen multiple times.
I hit my
Yes.
head multiple times. I'm not encouraging anything.
Oh, so the more you hit is like an amplifier. That's what's going on.
Yeah,
Yes.
I
like
see.
Albert Einstein kind of thing.
What the hell?
Yeah.
Yeah.
Really? So all you saying intelligence. I spelled intelligence wrong. You see, I hit my head too much times. Intelligence is proportional to hitting your head.
But even
That,
so,
that's
we
what
Yes.
I'm
on the
saying.
yeah, but even so, we're on the topic of physics. Isaac Newton, the apple fell on his head, and then he created the
Yes, and
whole
Oh,
that's
you're
subject.
yes.
cooking, you're cooking, you're
He
cooking, you're
created the
cooking.
whole
You're cooking.
subject.
Let's hear him cook.
So yeah,
Oh,
so literally something need to hit your head in order for you to collect all that information. Like, I'm
It
talking
just
truth
has
or I'm
to be
talking truth.
something good, you know?
That
Yeah,
theory
like
needs to be studied.
mm-hmm.
Rajiv, I'm gonna make a little thesis here. Rajiv hitting his head 2 times. Shayna being hit by a rock. Isaac Newton on an apple.
So at the end of the day, it just starts off with something hitting your head. Yeah, I see. See.
I will put that in. I'll put that in.
Before my exams, I'll hit my head with my book. Maybe it will
Yeah,
help.
maybe it'll help.
Maybe like the information from the book might transfer to your brain.
Yes.
Right. And I'll be credits to Jaden Williams. I think your last name is Williams.
Yeah.
Oh. Yeah. So
I feel like if somebody sees it with all context, they'll be like, what is we're talking about?
they'll be like, this man can't be a teacher. What are you writing this on the screen for?
In a couple of years, when Sir to school, they'll watch back and be like, wow,
Mm-hmm.
my name was in
Yeah.
two notes.
I feel like we need to print this out and give it to say for like a Christmas gift or something.
Something, so yeah.
Yeah, frame it.
Oh, I see, like, I did post this thing on my status, right? One of my students, she did write best teacher ever. And like years after, I now realize she spelled my name wrong.
Oh
Oh
my
my god. Yeah, I saw
Yeah,
that.
I
yeah,
saw it on TikTok.
Oh, Black, that's one of my
She-
favorite students. Can't believe she spelled my name wrong.
She was learning.
Yeah, but English too, apparently.
Oh my.
Blow.
I will troubleshoot that. I will tell you. You had to get some English lessons now. English vibes. Truth be told, though, I could never teach English. I can't. Really can't. I could never. No, me and that. Right? So just to like give all some context of this question, like before I go, this question wasn't as hard as it seemed. Really wasn't as hard as it seemed. So like, they want me to figure out the energy required to melt ice. If you're melting the ice going from and to melt ice that would be a state transition, and it'd be going from ice to water. So, Karina, you should know this, right? There wouldn't be a change in temperatures, but there's a change in state. So you have to use E is equal to MLF. So for the very first question, it would be E is equal to the mass. The mass was the mass of the ice was 0.40. No, it was 0.08. All you do is just multiply that by LF, which is 3.4 by 10 to the power 5. That's how you calculate the first question. The second question, so I'll give you all the hints, right? I'll give you all the hints as to how to solve these questions. And you'll do it for homework. So Zachary, pay attention, right? It's just hints to be able to solve these questions. So for the first question, you have to use E is equal to MLF because it have a change in state. The second question, the energy gained by the melted ice. Zachary, there?
Yes, sir.
All right, so Zachary, like I say, I give any hints now. So like after class, I'll go and give the question a try with these newfound hints. Right. So energy gained by the melted ice to warm it from 0 to 8. So for the second part, you're going to use Q or E. You're going to use E is equal to MC. Either one is fine. You can say Q is equal to MC delta T, or you can say E is equal to MC delta T is fine. Right? The energy gained by the melted ice. So, according to the question, what was the temperature of the ice originally? Could somebody tell me what was the temperature of the ice originally?
0 degrees.
And after the ice completely melts, what temperature did it settle on?
0 degrees.
No.
Oh, I thought you were talking about the ice.
Right. But get this right. when the ice completely melted, it was able to change the temperature from 29 to 8. So the change the ice would have experienced would be 8. It would be a change in temperature of 8. I know it's a little confusing, right? But that would be the energy gained by the melted ice. So for part B, you'd use E is equal to mc delta T, and the change in temperature for the ice would have been 8. Right? Part C, the energy lost by the lime juice. You'll have to use. Okay, for this one, let's see. This question kind of weird. That's interesting. Because I suspected I would have had to find the specific heat capacity first. Okay, so the answer for part C would just be the sum of A and B. Because think of it like this. This will be the energy to go from ice to water. So that's a certain amount of energy. And then this will be the energy it would take to go from ice to water at 8 degrees Celsius. So this will be a certain amount of energy here, and this will be a certain amount of energy, right? And the heat in the lime juice would be taken, it'd be extracted. And so the answer for part C would just be the sum of A and B. And part D, the specific heat capacity of the lime juice. If you know the total energy, that would be equal to the mass, right? C delta T. You know what the mass of the lime juice is. You should know what the total amount of energy is, right? And you find it for the specific heat capacity and the change in temperature. What was the change in temperature at the end? Could somebody tell me what was the change in temperature of the lime juice? Does anybody know? What's the change in temperature of the the lime juice? Zachary, what was the change in temperature of the lime juice? Do you know?
21 degrees.
Yeah, 21 degrees. So let me just put little hints, right? So for part B, you had to use E is equal to mc delta T. For part C, you're gonna combine part A and part B. Part D, you're gonna use E is equal to mc delta T again, right? And the energy you're gonna use will be the total energy, so A plus B, right? And the change in temperature will be 21 degrees. So best of luck, guys. And the change in temperature here would be 8 degrees Celsius. So I'll send this and you all will give it a try. Let me just explain what I'm going to do in the next class. So in the next class, we're going to look at heating curves and cooling curves, right? Specific latent heat. And yeah, we should be done with this aspect of thermal physics. The next part is gas laws. Did you all ever do gas laws in schools yet? Let me know. So like Boyle's, Charles, pressure law, combined gas law, ideal gas law. Okay, cool. So that's if we have time, we will move on to this. But I don't want to end off the year starting a new topic. I want to probably just wrap up on everything we did for the year, right? I don't want to move on to anything new and have that, high end. Don't want to do that. So yeah, it kind of sad. We're gonna have the last class for the year, right? If it's one thing you learn from class, is that the theory of hitting heads. There's one thing you learn. Credit to Jaden Williams for that. But yeah.
Well,
I will see you guys in the next class. Will you have any questions at all regarding thermal physics? Let me know if you guys have any questions.
sir.
Okay, so guys, I trust that you all will make the appropriate notes. Please copy down the diagram for the calorimeter, and please copy down the diagram for the method of mixtures. They will ask that. They will ask for the experimental setup. and they'll ask you to draw the experimental setup. Yeah. So anyways, guys, thank you for coming to class today. I will see you all sometime very soon. So later, guys. Bye-bye.
Bye, sir.
Guys.